Hi, this is Raqib Khan, and today I am going to present a Spectroformer, a multi-domain Curie cascaded transformer network for underwater image enhancement. Underwater image enhancement algorithms play a very important role to explore the underwater environment. But because of uneven illumination and the scattering of light, the captured underwater image suffer with the various quality degradation, such as poor visibility, poor contrast, and the haziness in the underwater images. So these degradation have directly impacts on its applicability and its interpretability. So that is why the underwater image enhancement is one of the important pre-processing tasks for further application. The enhancement of underwater image primarily focus on the enhancement of the crucial details, that is they improve the visibility and dehaze the images and the improve the color contrast or to restore the colors. Motivation and the contribution of this work. So first motivation, the transformer-based architecture perform well in the image restoration task, especially for the underwater application. But its effectiveness has primarily focused on the spatial domain only. But the underwater image acquisition taps into both frequency domain and as well as a spatial domain to extract the valuable insight from the captured features. In the frequency domain analysis, high frequency component the fine details and the low frequency component contains the overall pattern, while the spatial domain focus on the pixel values and the position of the scene understanding. So integrating of both domain, frequency and as well as the spatial domain will improve the accuracy, visibility, color accuracy, and the contrast, and it perform well in the even very challenging underwater conditions. So with this motivation, we propose a Spectroformer, a multi-domain Curie cascaded transformer network for underwater image enhancement. And we propose a multi-domain Curie cascaded attention mechanism for integrating the transmission and the illumination features. And we propose a spectrofusion based attention block to transfer the feature from uh, encoder to corresponding decoder. We propose a hybrid Fourier spatial upsampling block to significantly improve the feature resolution. This is the overall architecture of the spectroformer. So in this spectroformer, we have multi-domain Curie cascaded transformer. So in that transformer, we have multi-domain Curie cascaded attention. So in that there are two attention. The first attention is the attention map 1 that is calculated in a spatial domain only, and then this is the second attention map that is calculated by taking the Curie that is processed in the frequency domains, and this is in the cascaded form. That's why it is called multi-domain Curie cascaded attention. And the second is the to process the feature in the Curie in this frequency domain. We have the frequency domain feature processor that takes the feature in the spatial domain and pass in the frequency domain, and then apply the 1:1 convolution GALU, and then again 1:1 convolution, and then take back into the spatial domain through the IFT back. And this is the downsampler to downsampling. So it uses the pixel supply techniques, and this is the upsampler that is hybrid Fourier spatial upsampling that takes the advantage of both spatial upsampling, that is pixel suppling techniques, and this is the frequency domain upsampling, that is deep Fourier upsampling. So that improve the resolution by taking the advantage of both spatial domain upsampling and as well as frequency domain upsampling. And third is the here, so the spatial spectrofusion attention block that is used to transfer the feature from the encoder to corresponding decoder with attentive way. So and we'll discuss more detail in the next slide about this block. So this is the spatial spectrofusion based attention block that integrate both the spatial feature and as well as uh, frequency domain features, and then pass these features to the for attention. So in the attention, we have the adaptive kernel convolution. That is the that means the kernel size depends on the channel of the input features. So this is the overall attention block that is used to pass the attentive feature from the encoder to corresponding decoders. In our experiment, we have used two kinds of datasets, the synthetic dataset and the real world dataset. In synthetic dataset, we have used the UIB datasets that is used to train the model. So in that UIB datasets, there are 800 images for the training and 90 images for the testing. But we apply the some augmentation techniques and make the training images for 4,800. And for the validating our network, we have used three types of real world data set, that is Squid, UCCS, and the U45. And our method overperform in all three real world data set. That shows our effectiveness of our proposed model. For the real result analysis on the UIB synthetic data set, so we have two kinds of comparison. One is quantitative comparison. So we compare our results with the existing state-of-the-art method. So we have the highest PSNR value, highest SSIM value, and highest UIQM values. And for the qualitative comparison, we can see the input images, and these are the existing state of the arts results, and this is our results. So we can see that our result is very close to the ground truth. That shows the effectiveness of our model. So result analysis on the real world data set. So this is the quantitative comparison of our model with the existing state of the art method. So in this U45 data set, we have the highest UIQM, UISM, and NIQ value, and second best in the bricks. Whereas in the UCCS data sets, we have the highest UIQM value, second best UISM value, and NIQ second best in the NIQ value, and the highest in the and the best result in the brisk. So this shows that the overall performance and the effectiveness of our model. This is the result analysis on the real world dataset, and here we compare the qualitative comparison with the existing state-of-the-art method on the UI Squid dataset, U45 dataset, and UCCS dataset. So we can see in all these dataset our results is looking visually pleasing. In all the dataset we can see here. So this is the application of our proposed method for the depth estimation. So here we have the input images, that is corrupted images, and its corresponding depth. So these all are the depth of the images of the resulting images of the existing state of the art method, and this is ours. So we can see that our results, the depth of our enhanced images results, giving the very fine details as compared to the other existing state of the art methods. To demonstrate the effectiveness of the proposed individual component, we have performed the evaluation studies. So we have here B is the baseline, C is the multi-domain Curie cascaded attention, spatio spectrofusion based attention, and then hybrid Fourier spatial upsampling. So here we can see the performance of the each individual component in the quantitative way, and also we can see the qualitative way as well. So this is the output of all the network settings. Now, finally, summary of this proposed work. So we propose Spectroformer, a multi-domain Curie cascaded transformer network for underwater image enhancement. We propose a multi-domain Curie cascaded attention mechanism that integrates localized transmission feature and the global illumination features. A spectrofusion based attention block is proposed to transmit the attention enhanced feature from the encoder to corresponding decoder, and effectively boosting the performance and the features of enhancement. And a hybrid Fourier spatial upsampling is introduced that uniquely combines the Fourier and the spatial upsampling techniques to effectively enhance the feature resolution. And finally, we have performed the several evaluation studies and the on the real world, and as well as the synthetic data sets. So for any further detail, kindly visit on this on here, and uh, and you can mail us on this email ID. Thank you very much.